find this constant, we're going to use what is called the Rossland approximation. The Rossland approximation considers the equation of radiative transfer and is appropriate in the deep interior, where the medium is optically thick and the source function approaches the Planckian. So you can write this. If you divide both sides by kappa rho, you have cosine theta over kappa rho, di dz is equal to b minus I. So you solve this for the intensity. Now, this doesn't completely solve for the intensity because you have the intensity on one side and the derivative of the intensity in z on the other side. But, and this comes the second part of the Rossland approximation, is to say that even though the intensity field is not exactly the Planckian, its variation in the vertical direction is going to be like the variation of the Planckian. So you can then write the Rossland approximation for the intensity. And let's reinstitute here the frequencies. So the intensity is the Planckian minus the coefficient times the derivative of the Planckian in z. You can see here that this looks a bit like the definition of the optical depth. In fact, the Rossland approximation is equivalent to a linear truncation of the Taylor expansion of the intensity at optical depth equal 1. To see this, consider here the Rossland approximation and do the Taylor expansion of the intensity at some point z, state that the intensity is the Planckian at a point z naught. Let me drop the knee here for clarity. And then the terms here of the expansion. So let's ignore now the second order and the third order term. I have only the linear term. And I'll use the definition of the optical depth, which is the tau is equal to kappa rho dz over cosine theta. If you write this in terms as dz is equal to d tau cosine theta over kappa rho, and then integrated from z naught to z, which would mean then the integral from tau naught to tau, this would be then z minus z naught is equal to tau minus tau naught cosine theta kappa rho. So if you plug in back there in the Taylor expansion, this expression for z minus z naught, what you have is t minus t naught cosine theta kappa rho dB dz. Substitute this tau minus t naught by delta tau. Actually, there should be a minus here, sorry. So here you see the equivalence between the Rossland approximation and the Taylor expansion. They are identical if delta tau is equal to 1. When we're talking about the Rossland approximation, we're talking about the intensity field in a depth that is optically thick and the radiation up to one mean free path away from the location where you're measuring. That means that if you are away by one mean free path, this is a valid approximation when the radiation field is isotropic over distances that are comparable to or less than the radiation mean free path, such as you expect in local thermodynamical equilibrium. So the Rossland approximation is a good approximation for the intensity field in local thermodynamical equilibrium. It describes a variation. The Rossland approximation describes a variation of the intensity field when you are interested in small inhomogeneities up to linear order from the intensity being equal to the Planckian. Now, this is a good approximation for the intensity field of a star because we know that locally the field is isotropic. Locally, the field is in thermodynamical equilibrium, but we know also that there is a large scale temperature gradient that is carrying the flux. In this approximation, the linear term that is away from the isotropic term describes this temperature gradient that is carrying the flux.